Hello, welcome to Chapter 5.2, Figure-8 Numbers. Figure-8 numbers. The figure-8 numbers make common figures or shapes. There are triangular numbers that make triangles or pyramids, square numbers that make squares, pentagonal numbers that make five-sided shapes called pentagons, and more. You have already seen the square numbers, so we'll start with those. The square numbers are perfect squares, 1, 4, 9, 16, 25, etc. We write S1 to indicate the first square number, S2 for the second square number, and so on. The formula to find the square number is Sn is equal to n squared. We will go into more detail about figure-8 numbers on the whiteboard.
Figure-8 numbers are numbers that take on shapes. So you can have triangles, you can have squares, you could have pentagons, etc. Okay? So they're numbers that take on certain shapes. As we saw earlier, perfect squares, okay, if you have are 1, 4, 9, 16, 25, etc. So that means we write each of these, we call them S1, I'll call this S1, I'll call this one S2, I'll call this one S3, I'll call this one S4, I'll call this one S5, and so on. So the formula for a perfect square would be Sn is equal to n squared, where n, okay, is Sn, so n would be 0, 1, 2, 3, 4, 5, etc., and then you square that. So for example, if you have n is equal to 3, then S3 is equal to 3 squared, which would give us 9.
We can draw the square numbers as square shapes. S1, S2 is equal to 4, S3 is equal to 9, S4 is equal to 16, S5 is equal to 25. So let us go over to the whiteboard and look at this in a little bit more detail.
In pictorial form, we can put a little unit square to be S1 is equal to 1, and then we can break it up into 4. A bigger square, meaning add to that, S2 is equal to 4, S3 is equal to 9, etc. Another way to look at this would be to start at S1 as a point, and then when you go to S2, 1, 2, 3, 4 would be S2. So you have 1, 2, 3, so you just add on little points. S9, well, we start out with our 1, 2, 3, 4, and then what we can do is we can go 1, 2, 3, 4, 5, and if we count that, we can go on, we can see that this is S9. S3. So this is S1 is equal to 1, S2 is equal to 4, S3 is equal to 9, and then we can do S4, and I'll draw it here as it is in your workbook or PowerPoint. So you have 4 up here, 1, 2, 3, 4, 1, 2, 3, 4, and this would be S4 is equal to 16. And then I'm going to just take this and continue it on. So I start out with our 9 points. S4 will be equal to, so we have 1, 1, 2, 3, 1, 2, 3, 4. We had that for S9, and now in order to get the next one, what I'm going to do is put points and have 1, 2, 3, 4, 1, 2. And we see now, if we count all these dots, we end up having S4. And that would be indeed 16. So one of the things we could do to see the shapes more clearly and see that indeed it looks a lot like what we have above. So we start out there, and now we have the box, okay, with the 4 points. And here we have our 9 points. So this is our 9 points. It looks a little bit different, okay. But really here we're focusing on the points, where in this version we're focusing on the boxes. So whatever you like, so long as you're very careful that you're just counting points rather than boxes if you're doing it this way. If you're doing it this way, you count boxes, meaning you're using a piece of graph paper and you're actually using the boxes. In this case, you're actually counting the points on the shapes, so that will be a little bit different. So let me draw this back again to what it was, so it's clear. Here you're counting the points, and here nine points, and this one is 9 squares. Let me make that a little bit clearer. So if you prefer to use graph paper, this would be S3, which would give us also 9. And this is 9 boxes. So those are called the square numbers. Now, of course, you can do this for many other shapes, and we'll get into that in the next examples.
In example number 1, we're asked to use the formula to find the 6th square number and draw the picture. So let us go over to the whiteboard and work this one out in detail.
The formula was Sn is equal to n squared. Now we have n, they tell us, is 6. Because they're asking us for the 6th square number. That means n would be 6. So now we put S6 is equal to 6 squared, and we get 36. They also ask us to do the picture. So I will do it using the dot method. So I'm going to start off with S1 as 1 dot, S2, there's S2, then I go on to S3, then I'll go on to S4, Then I'll go on to S5. I'm just going to erase this to make a little room and rewrite it. So we found earlier that S6 is equal to 6 squared, which was 36. So I'll put that on the side here. And then we have, so we did up to S5, 1, 2, 3, 4, 5. Now we'll do S6. Okay, and then I count, see if it conforms to what I have here. So I'll count the number of dots. So I have 1, 2, 3, 4, 5, 6 dots here. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And indeed, I do have 36 dots that conforms to our 36 here, just like the problem asks us for, or the example is showing us.
Reviewing what we did on the whiteboard quickly, we replaced the n in the formula with the number 6. S6 is equal to 6 squared, which is equal to 36. And the picture will be a 6 by 6 square if you do it with dots or you do it with squares, depending on how you want to do it. In example number 2, we're asked to find the successive differences for the square numbers. So let us go over to the whiteboard to see how this would be done.
We're going to say n is equal to 1, 2, 3, 4, 5, 6, 7. And then we know the square numbers. Well, for n is equal to 1 is 1. 4 for n is equal to 2 is 4. For n is equal to 3 is 9. For n is equal to 4 is 16. For n is equal to 25 is equal to 25, 36, and 49. Now we're going to take the successive differences between these two. So, well, we're going to see that we have to add on 3 here. We have to add on, in order to get 9, 4 plus 5 is equal to 9. 9 plus 7 is equal to 16. 16 plus 9 is equal to 25. 25 plus 11 is equal to 36. And then finally, 36 plus 13 is equal to 49. Now, we see we don't have it all constant here. They're still all different. So we want to make sure we get a constant number. So now we have to do another row. So let's see what happens when we do the series in the next row. Well, we go from 3 to 5. So in order to get, what do we have to add to 3 to get 5? We add 2. Then, what do we have to add to get from 5 to 7? We get 2. What do we have to add to go from 7 to 9? Plus 2, and so on. So now it has stabilized out at 2. And what this tells us, because if it stabilizes out at this level, it is linear, which is the y equals mx plus b form. But since it's stabilized here, meaning all the numbers are constant here, this means it's quadratic. So that means that the highest number in it will be x squared, or the highest power will be in terms of squared. And indeed, since they're called the squared numbers, we know that this is true.
Reviewing what we just did on the whiteboard, we wrote our square numbers, and then we did the successive differences, and we found out that we didn't get a constant number of differences. So we did it again, and then we finally got a constant number, and that's when we knew where to end. But we had to go through it twice, which means that if it was once that we had to go through it and got a constant, it would be linear. But since it was twice, that means it's quadratic, which means that it's squared, which of course makes sense since these are the square numbers. A linear equation, which graphs a line with x to the first power as the highest power term, will have one row of successful differences, which will remain the same each time. That difference is the slope of the line. A quadratic equation, which graphs a parabola with x squared as the highest power term, will have two rows of successive differences before we get a difference that stays the same each time. An equation with x cubed as the highest power term will have three rows of successive differences before the differences stay the same each time. To find the equation, we would probably need to use calculus using the derivative. The next type of numbers we're going to deal with are triangular numbers. So let us go over to the whiteboard and discuss what triangular numbers are.
And of course, triangular numbers, by its name, make triangles. So we can use the boxes as if we were the boxes. So we can draw T1, T2, T3, T4, okay, and this is T4. So this is 1, this is 3, and we count the number of blocks, 1, 2, 3, 4, 5, 6. And this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is 10. So here we have 6, 1, 2, 3, 4, 5, 6, 10, and 3. Okay, so we can draw it like that. The other way that we could do this is like I did earlier. We can do it with the dots. So there are two different ways of doing these that I'm familiar with. So we can start out with T1, which is one dot. That would be our T1. And then we can go, grab my room, which is one dot. Then we can go to T2. So we're just going to add a layer here, a triangular layer. So that will give us T2. As you see, it also is 3. And then we add on another layer. Here's our old layer. And then we add on the third layer. And that gives us T3. And then we add on a fourth layer, Just drawing in the other layers. And then we forget on the fourth layer. So there we have the fourth layer, and as you see, indeed this is one dot. Here we have 3 dots. Here we have 6 dots. And here we have 10 dots. T4, 10 dots. So those are the 2 ways in which we could represent this.
Reviewing what we just did on the whiteboard, we found for triangular numbers we write T1 to mean the first triangular number, T2 to mean the second triangular number, and so on. So drawing with blocks, we use T1 with 1 block, T2 will give us 3 blocks, T3 will give us 6 blocks, T4 will give us 10 blocks, and so on. So the first triangular number has 1 block, T1. The second triangular number has 3 blocks, T2. The third triangular number has 6 blocks, T3. And the fourth triangular number has 10 blocks, T4. For example number 3, we're asked to see if you can draw the correct picture of T5 by copying the picture for T4 and adding 1 more layer of blocks on the bottom row. So let us do this one on the whiteboard.
So of course you can do it with the blocks, but I'm going to add on my other layer. I'm going to erase my blocks, and I'm going to add on my other layer with my dots. So here we go. And I'm going to add on another layer of dots to see what my answer would be. So here I go. So here I have So I added on 1, 2, 3, 4, 5 more dots. So my T5 will be equal to 15. So you see what I did is that by adding another layer, I got the next set of the next part in the sequence.
So now I'm going to do it using blocks, because what I did on the whiteboard, I actually just used the dots. So if I use the blocks, I'm going to add 5 blocks to the bottom. So here I have my original T4, and I'm going to add 1, 2, 3, 4, 5 blocks to the bottom. And this will give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 blocks, just like I did on the whiteboard, but I did with dots, and I got 15 dots. So either technique you use would be fine. In example number 4, we're asked to find the successive differences for the triangular numbers and use them to find the 5th, 6th, and 7th triangular number.
Let's put n is equal to 1, 2, 3, 4, 5, 6, 7, and we'll end at 7 since that's as far as we're asked for, because we want to find the 7th triangular number. Well, we found that the first triangular number is 1, then we had 3, then we had 6, and then we had 10. And now we find we're going to do how much do we have to add go from 1 to 3? We have to add 2. How much do we have to go from 3 to 6? We add 3. How much do we have to go from 6 to 10? 4. So we start seeing a pattern emerging. Now earlier we found in our former problem, we found that when n is equal to 5, T5 is equal to 15, and as we can guess, this will go up to 5. That will go up to 5. But we want to go up to 7. So we're going to see what we could figure out. Well, 1, 3, so we're going to see what this one is. So we see this is 1, 1, 1 are the success. So it stabilizes here. And now we want to go up. So since this is going 2, 3, 4, 5, we're going to guess the pattern of the next one is going to be 6. So 15 plus 6, this will be 21. And again, we're going to guess based on the pattern so far, we'll guess that we'll have to go up 7 to get the next number, which is 28. So let's see if it maintains and becomes consistent. Well, here we go, the difference between, so 5 we have to go up, 5 we have to go up, and we see it stabilizes on the second line there. So one can ask, well, what does that mean? Well, again, as mentioned earlier, that means that somewhere along the line there is something of the form n squared somewhere in the formula.
So let us review what we just did on the whiteboard, and we found that the triangular numbers 1, 3, 6, 10, 15, 21, and 28, when we use successive differences, we got 2, 3, 4, 5, 6, and 7. And that means that they went up by 2 to 3, 3 to 4, 5 to 6, 6 to 7, that they went up by 1 if we did a third row. So that means since we have 1, 2 rows, that means somewhere along the line there's a square in our formula. As indicated, there is a formula for triangular numbers just like there is for square numbers. So for the triangular numbers, the formula is Tn is equal to n times n plus 1 all over 2. Now, if we use our distributive property and multiply in the n, we see we get n squared plus n over 2. So the highest power is the second power, as expected by the fact that it took 2 rows for the difference to remain constant when we did it on the whiteboard. In example number 5, we're asked to use a formula to find the 6th triangular number. So let us go over to the whiteboard and work this one out.
So we're going to use our formula to find the 6th triangular number. That means n will be equal to 6. So we have our formula, Tn is equal to n plus 1 over 2. So what we want to do is wherever we see n, we're going to put 6. So we have t to the 6 is equal to 6 plus 1 over 2. And remember, we have to make sure we use our order of operation, or we can just multiply it in, but it's much easier if you use your order of operation and do what's inside the bracket first. So you have 6 over 7 divided by 2, and then we see 2 goes into 6, and that's 3, and then we get 3 times 7, and it turns out indeed 3 times 7 is 21, as we saw in the when we did the exact sequence.
Reviewing what we just did on the whiteboard, we used the formula and we plugged in n is equal to 6 and we got the answer to be 21. In example number 6, we're asked to use the triangular number formula to find the 7th triangular number. So let us go over to the whiteboard and work this one out.
When n is equal to 7. So we write our triangular formula, number formula, over 2. And we see wherever we see an n, we put a 7. Divided by 2. And I'm just going to add the ones inside the bracket first. You can do all that, but this is easier. And I see 2 goes into 8. And then I end up with 7 times 4, and that gives me 28, just like I found earlier when I did the sequence.
Let us review what we just did on the whiteboard. For the 7th triangular number, we let n is equal to 7 in the formula, and we plugged 7 into the formula, and we got 28 after working it out. As mentioned, figure 8 numbers come in many different shapes. So we just did the triangular numbers, we've already done the square numbers, and as I said, they also are pentagonal numbers. Each of these figure 8 numbers has its own formula. So for any natural number n, the formulas are given by. The nth triangular number is given by t sub n is equal to n times n plus 1 over 2. The nth square number is given by s sub n is equal to n squared, and the nth pentagonal number is given by p sub n is equal to n times 3n minus 1 all over 2. In example number 7, we're asked to use the formula to find the 6th pentagonal number. So let us go over to the whiteboard and work this one out.
The pentagonal formula, as we just saw, is p sub n is equal to n times 3n minus 1 all over 2. And we're being asked to find the 6th one, which means n will be equal to 6. So that means p of 6 is equal to 6 times 3 times 6 minus 1 over 2. And then we proceed to do the arithmetic here, So we have 3 times 6 minus 1. So we'll put the 6 out here. So that means we're going to have 6, 12, 18 minus 1 over 2. So that means we're going to have 6 times 17 over 2. So that means we'll have 3 times 17. And that will give us 51.
Let us review what we just did on the whiteboard. We used the formula for the pentagonal numbers, and we plugged in wherever we saw n. We plugged in 6, and we got, when we worked it all out, p sub 6 is equal to 51. Thank you very much. I hope that you enjoyed this video. Take care, be well, and goodbye for now.